At the center of our Milky Way galaxy, hidden behind clouds of dust and stars, lies something we cannot see with our eyes, but which has the mass of millions of suns. This mysterious object is called Sagittarius AAR, and it's a supermassive black hole. Unlike the monsters powering distant quasars and active galaxies, Sagittarius AAR barely makes a peep, but its silence is misleading. Just beneath the surface, there's a storm of magnetic fields, flares, and extreme gravity that stretches the limits of physics. This is the story of how we discovered it, how we photographed the unseeable, and what this black hole has taught us about the universe, the galactic bulge that hid the truth. For a long time, even after people began building telescopes and studying the stars with scientific tools, the center of the Milky Way remained hidden. Astronomers could map parts of the sky, track planets, and chart the motion of stars. But something was still in the way. Whenever they turned their instruments toward the thickest part of the Milky Way, toward the constellation Sagittarius, they ran into a wall of light and shadow, of gas and dust, and of stars packed so tightly that they blurred into each other. This area, now known as the galactic bulge, is one of the most crowded regions in the entire Milky Way. It is a huge central swelling made of hundreds of billions of stars. From Earth, it lies in the direction of the galactic center. But seeing through it is not easy. In fact, for centuries, it was nearly impossible. When people look up at the Milky Way with the naked eye, they see a pale band stretching across the night. It looks almost like a faint cloud, but that band isn't made of cloud or mist. It's made of stars. So many stars packed so close together that they blend into a soft glow. That glow gets brightest near the center of the Milky Way. But along with the brightness comes something else: darkness. This darkness is not the absence of stars, it's the presence of dust. All across the galaxy, floating between stars are clouds of interstellar dust. These clouds are made of tiny particles, bits of carbon ice and rock left over from older stars and drifting slowly through space. While these particles are small, they're spread out over such huge distances that they can block light, especially visible light, the kind our eyes and early telescopes can see. That's the key problem. For most of history, telescopes worked only in visible light. They were built like giant eyes, collecting light from stars and focusing it into images. But visible light is easily blocked. When it tries to pass through dust, it gets scattered or absorbed. And nowhere in the sky is there more dust than in the direction of the galactic center. Astronomers would look towards Sagittarius and see nothing but confusion. A thick mess of stars broken up by dark streaks like smoke smeared across the sky. The stars closer to Earth were visible, but behind them, darkness. The light from the true center of the galaxy couldn't reach us. It was as if someone had drawn a curtain across the middle of the Milky Way, and the bulge itself made things worse. Unlike the flat disk of stars that stretches out like a pancake around the galaxy, the bulge is swollen and round. It's thicker and denser than the outer regions. Stars in the bulge are packed closely together, overlapping and shining in all directions. But because there are so many of them, and because of all the dust mixed in, their light becomes hard to separate. The signals are there, but they get lost in the noise. This made the center of our galaxy one of the most mysterious places in the sky. People could see the outer arms of the Milky Way, and they could map stars in nearby regions, but they couldn't see what lay at the heart. They didn't even know if there was a heart. Was the galaxy spinning around something? Was there a true center at all? Or was it just a loose collection of stars with no fixed point? Some early astronomers believed the sun was near the center of the Milky Way. When they looked around, they saw stars in every direction, so they guessed we must be somewhere near the middle, but that was only because they couldn't see past the dust. Their view was blocked in the direction of the real center, so it looked like the stars were evenly spread out. In the 18th and 19th centuries, astronomers like William Herschel tried to map the shape of the Milky Way using star counts, simply counting how many stars were visible in different directions. They tried to figure out the structure of the galaxy. But they didn't know about interstellar dust, so when their maps showed more stars in some directions and fewer in others, they assumed that meant the galaxy was shaped unevenly. In truth, the dust was hiding much of what they needed to see. It wasn't until the 20th century that things began to change. New kinds of telescopes were developed, ones that didn't just use visible light. Scientists realized that if they wanted to see through the dust, they needed to use forms of light that could pass through it more easily, like infrared and radio waves. These types of light are invisible to our eyes, but they carry information just like visible light does. And unlike visible light, they can travel through dust without being scattered or absorbed as much. With infrared telescopes, astronomers could finally start to peer into the galactic bulge. They could see stars hidden behind the clouds. They could begin to map the true shape of the center. And with radio telescopes, they picked up signals from deep within the galaxy. Waves of energy coming from strange sources that had never been seen before. One of the most important discoveries came in the 1930s and 1940s when radio astronomers started detecting a strong signal coming from the constellation Sagittarius. It wasn't a normal star, and it didn't look like anything familiar. It was a powerful source of radio waves coming from the very center of the Milky Way. They called it Sagittarius A. At first, it was just a bright spot in radio images buried deep inside the galactic bulge. But over the years, as instruments improved and scientists studied the region more closely, they began to realize that something very strange was there. Something massive, something invisible, and something pulling stars around it at incredible speeds. But even then, the dust and gas made the study of the galactic center difficult. Astronomers had to build better and better instruments, working from mountaintops, balloons, and eventually space to get clear views. The bulge remained one of the most crowded, chaotic, and complex places in the galaxy. What made it even harder was that stars in the galactic bulge move fast. They're not slowly drifting. They're whipping around the center in tight, fast orbits. Tracking those motions requires extreme precision. You have to watch the same stars for years, taking careful measurements to understand their paths, and only then do the patterns begin to appear. All this, the dust, the density, the movement, combined to keep the truth hidden for most of human history. While ancient people made up stories and early scientists guessed its shapes, the real center of the Milky Way remained blocked by its own structure. It was there all along, behind a glowing, swollen mass of stars and a thick fog of interstellar material. Only by looking with new kinds of eyes could we begin to see it for what it really was. The radio signal that changed everything. In the early 1930s, a young engineer named Carl Jansky was working at Bell Telephone Laboratories in New Jersey. His job had nothing to do with astronomy. He was simply trying to solve a problem for long-distance radio communication. At the time, radio was growing fast. Ships, stations, and countries all depended on clean signals, but there were strange background noises, static that couldn't be explained. Jansky was asked to find out where these noises were coming from. To do this, he built a strange-looking machine. It was a large rotating antenna. Some called it a merry-go-round because it sat on wheels and could be turned to face different parts of the sky. It was designed to pick up radio waves in the shortwave band around 20.5 MHz. That's much lower in frequency than visible light, but it carries useful information for communication. Jansky spent months collecting data. He found that some of the static came from nearby thunderstorms, some came from distant lightning, but there was one source of noise that came and went in a regular pattern about once every 24 hours. At first, he thought it must be related to the sun, but over time, the timing didn't match exactly. It came roughly 4 minutes earlier each day. That's when he realized this source wasn't tied to the Earth's rotation relative to the sun. It matched the Earth's rotation relative to the stars. In other words, it was coming from space. The direction of the signal pointed toward the center of the Milky Way. This was the first time anyone had ever detected radio waves from outside the solar system. It was an accident, a side effect of routine engineering work. Jansky's discovery was the beginning of radio astronomy. At first, the news didn't cause much excitement. Astronomers were still focused on optical telescopes and few understood the importance of radio signals from space. Jansky himself didn't continue with space research. Bell Labs moved on to other projects, and his antenna was eventually dismantled, but his discovery had planted a seed. A few years later, a man named Grotto Raber picked up where Jansky had left off. Reber was a radio engineer and amateur astronomer. He read about Jansky's work and decided to build his own radio telescope in his backyard. He constructed a large parabolic dish about 9 meters across and began scanning the sky for radio waves. Reber confirmed Jansky's results and mapped the radio sky for the first time. His maps showed strong radio signals coming from the same part of the sky. Through the 1940s and 1950s, more scientists joined the field. Radio astronomy started to grow. New antennas were built, larger, more sensitive, and able to cover a wider range of frequencies. These instruments revealed a sky that was invisible to the eye. Objects that looked dark in visible light sometimes glowed brightly in radio waves. the center of the Milky Way, once hidden behind dust, now began to speak in a new language. By the 1960s, radio telescopes had become powerful tools. Scientists could study the structure of the galaxy in detail. They detected radio signals from gas clouds, supernova remnants, and even from other galaxies. But one spot remained especially interesting: the strong, compact radio source in the direction of Sagittarius. This signal, first noticed by Jansky, was coming from a very specific point. It was steady, strong, and located right at the heart of the Milky Way. It didn't flicker, and it didn't spread out over the sky. It was compact, confined to a very small area. That suggested it was coming from something small, but incredibly powerful. But even in the 1970s, no one knew exactly what it was. The signal was strong, but it wasn't easy to explain. It didn't match the patterns of known nebulae. It didn't look like a supernova remnant. To learn more, astronomers needed to watch how stars moved around this invisible point. But this kind of research took time. The center of the Milky Way is 26,000 light-years away. Stars there move quickly, but not so fast that their orbits can be tracked in just a few days or weeks. Infrared eyes open in a dusty darkness. In the second half of the 20th century, scientists began building instruments that could detect infrared light from space. Some of the earliest attempts were made using high-altitude balloons and aircraft. Earth's atmosphere absorbs a lot of infrared light before it reaches the ground. If you want to study the sky in infrared, you need to get above the thickest parts of the atmosphere. One of the key steps was putting infrared telescopes on mountaintops. In places like Mount Aya in Hawaii or the Atacama Desert in Chile, the air is dry and thin. That makes it easier for infrared light to reach the instruments. From these high points, astronomers began collecting the first clear images of stars and gas clouds hidden in the center of the Milky Way. Even early results were surprising. In regions that looked dark in visible light, infrared telescopes revealed clusters of stars. The heart of the galaxy was not empty. It was full of activity. What had once been a blank patch of sky now came to life. Still, ground-based telescopes had limits. The Earth's own heat and atmosphere made it difficult to get clear, uninterrupted data in certain infrared wavelengths. The next step was to go into space. In 1983, NASA launched the Infrared Astronomical Satellite, or IRAS. It was the first telescope to map the entire sky in infrared. Though not focused only on the galactic center, it showed just how much was hidden in the dusty parts of the sky. Whole regions that seemed empty in optical images lit up in the infrared, filled with young stars, warm dust, and strange sources of heat. Later space telescopes like the Spitzer Space Telescope, launched in 2003, would go much deeper, spending years looking into these hidden regions. Spitzer was especially important. With its sensitive instruments cooled to very low temperatures, it could pick up faint heat signatures from across the galaxy. One of its targets was the center of the Milky Way. Using its infrared eyes, Spitzer saw stars swirling close to a dense, invisible spot. This point, already known from radio signals as Sagittarius A star, was now under observation in a new way. While Spitzer worked from space, ground-based infrared telescopes were improving too. In Chile, at the European Southern Observatory's Very Large Telescope, a team led by Reinhard Genzel spent years tracking the motion of stars near the galactic center. At the same time in Hawaii, another team led by Andrea G.Z. used the KEK Observatory to do the same thing. They used advanced infrared cameras to pierce the dust and follow the paths of individual stars. Stars so close to the black hole that they completed orbits in just a few years. And these stars, called SARs, became key to proving what lay at the center of the Milky Way. One of them, named S2, moves in a long, fast orbit that brings it extremely close to Sagittarius A star. By watching its path over time, both research teams were able to calculate the mass of the object pulling on it. The result was stunning. The object had the mass of about 4 million suns, but it was packed into a space smaller than our solar system. It didn't emit light like a star. It was almost certainly a supermassive black hole. None of this would have been possible without infrared astronomy. The dust around the galactic core still blocked visible light, but in the infrared, the story became clear. Stars danced around an invisible force. Heat glowed where the eye saw nothing, and the shape of the galaxy's hidden center began to emerge, the stellar dance that gave away the secret. With the right tools, the movements of stars can be measured down to a fraction of a second of arc, a tiny angle in the sky, but enough to reveal dramatic stories when you're watching something over years or even decades. In the 1990s, a group of astronomers began doing just that. One of the teams was led by Reinhard Janel, working out of the Max Planck Institute in Germany. Another was led by Andrea G.Z. at UCLA in California. Each team used powerful ground-based telescopes fitted with advanced imaging systems to peer through the thick dust of the galactic center. Even with infrared telescopes, the challenge was immense. Earth's atmosphere creates constant interference, blurring images and making stars appear to shimmer or move randomly. To deal with this, astronomers used a technology called adaptive optics. It allowed the telescopes to adjust in real time, canceling out much of the distortion caused by the air above. Near Sagittarius, a star, they found stars moving at incredible speeds. These stars were whipping around a point in space like comets flying past a campfire. Some traveled at over 5,000 km/s. That's fast enough to go from Earth to the Moon in just over a minute. The key breakthrough came from watching these stars over time. One in particular, known as S2 or sometimes S802, stood out. It was a bright star, moving in a tight, fast orbit around a completely dark region of space. Over the course of just 16 years, S2 completed a full loop. No star this close to the center had ever been tracked for so long with such precision. S2 followed an elliptical path just like planets do around the Sun. That meant it was responding to gravity. From the orbit of S2 and other nearby stars, astronomers could calculate the mass of whatever was pulling on them. The answer was staggering: over 4 million times the mass of our Sun, all packed into a region smaller than our solar system. This left only one explanation: a black hole. Not just any black hole, but a supermassive one. It was the closest evidence we'd ever had of such an object. Black holes had been suspected and theorized for decades, but most of the time they had only been studied indirectly through X-rays from distant galaxies or simulations on computers. Here, for the first time, scientists were watching stars orbit around one, real stars moving in real time around something truly invisible. The evidence grew stronger with every passing year. More stars were tracked. Some had longer orbits. Some were even closer than S2. All of them pointed to the same central object. And even more, the orbits behaved exactly as predicted by Einstein's general theory of relativity. Their paths showed subtle changes, slight shifts in timing and direction that couldn't be explained by Newton's laws alone. This meant that the gravity near Sagittarius A star was not only strong, it was warping space and time itself. In 2002, Andrea G.Z.'s team published the first full orbit of S2. In 2008, Reinhard Genzel's group followed up with even more precise measurements. The results were nearly identical. Both teams working independently on opposite sides of the world had reached the same conclusion. There was a massive invisible object at the center of our galaxy. Its gravitational pull was shaping the motion of nearby stars. It could be nothing else but a black hole. As technology improved, observations became even sharper. By the 2010s, telescopes were capturing positions down to thousandth of a second of arc. That's like measuring the width of a human hair from several kilometers away. And these measurements kept confirming what we already knew. Sagittarius AAR was real. It shaped the space around it. It was a black hole. And yet in all this time we still had not seen it. Not directly. We had watched the stars move. We had followed the invisible footprints. But the black hole itself remained unseen. It would be some time before we found a way to look even closer. Different breeds of darkness from primordial to supermassive. When scientists first began to understand black holes, they were not looking at just one type of object. The idea of a black hole is simple in theory. A region in space where gravity is so strong that nothing, not even light, can escape. But the ways in which such objects form, grow, and behave can be very different. This is why astronomers often talk about types or classes of black holes. The one at the center of our galaxy, Sagittarius A star, belongs to the largest known class, supermassive black holes, but it is far from the only kind. Understanding the others helps explain just how unusual our galactic center really is. The smallest known black holes are called stellar mass black holes. These are the remains of massive stars that reach the end of their lives in violent explosions called supernovae. When a star several times heavier than the Sun burns through all its fuel, it no longer has the energy to push back against gravity. The core collapses, and if the mass is high enough, it becomes a black hole. These objects are small on a cosmic scale, sometimes only a few kilometers across, yet they hold more mass than our Sun. Despite their size, they can have powerful effects on their surroundings, especially if they pull material from a nearby star, forming an accretion disk that shines in X-rays. These stellar black holes are scattered throughout galaxies, including our own, and astronomers have found dozens of them through careful observation of such energetic emissions. A step up from these, though much harder to find, are intermediate, mass black holes. These range from hundreds to thousands of times the Sun's mass. Their origins are not fully understood. Some theories suggest they could form from the merger of multiple stellar black holes inside dense star clusters. Others suggest they might grow by steadily consuming gas and stars over long periods. They are rare in observation, which makes them interesting. Intermediate black holes may represent a missing link in the growth process between stellar mass and supermassive black holes. If these mid-sized objects are truly out there in large numbers, they might be the seeds that later grow into the giants we see at the centers of galaxies. Then, there are the true giants, the supermassive black holes. These weigh millions to billions of times the Sun's mass. Sagittarius, a star, is on the lighter side for this class, but even that makes it unimaginably powerful. Unlike stellar black holes which form from single stars, supermassive black holes could not have formed in one sudden collapse. They must have built their mass over time, possibly beginning with the collapse of enormous clouds of gas in the early universe, or from merges between smaller black holes and star clusters. Almost every large galaxy appears to have one of these giants at its core, and they play a major role in shaping their galaxy's evolution. There's also a type that exists only in theory: primordial black holes. These would have formed not from stars but from extreme density fluctuations in the very early universe just moments after the Big Bang. The idea is that tiny regions of space could have been so dense that they collapsed directly into black holes, some no bigger than an asteroid, others potentially much larger. If they exist, they could be scattered everywhere, perhaps even passing through our solar system from time to time without being detected. Some scientists have even proposed that certain unexplained cosmic phenomena could be the result of such ancient black holes. Another interesting theoretical type is the ultramassive black hole, an extension of the supermassive category. These would have masses exceeding 10 billion suns, and a few candidates have been observed in the centers of extremely large galaxies. Their size raises questions about how fast black holes can grow and whether there's a natural limit to their mass. Sagittarius AAR is firmly in the supermassive category, but it has some unique qualities. Compared to the largest black holes in the universe, it is relatively quiet. Many supermassive black holes are active, consuming huge amounts of material and producing blazing jets of energy that can be seen across cosmic distances. Our galactic center is currently in a low activity phase, feeding only occasionally and producing brief flares in radio, infrared, and X-ray wavelengths. This quietness makes it harder to study in some ways because it doesn't have the bright, obvious emissions that active galactic nuclei produce, yet it also makes it an ideal laboratory for studying the black hole itself without interference from the chaos of extreme feeding events. By comparing Sagittarius A star to other black holes, scientists gain perspective on its role in the galaxy. Stellar black holes might be more common, but their influence is local. They affect only their immediate surroundings. Intermediate black holes could bridge the gap, but they are rare in detection and uncertain in origin. Supermassive black holes shape entire galaxies, holding them together with their immense gravity and influencing the movement of stars and gas far beyond their event horizons. And if primordial black holes exist, they could provide clues about the earliest moments of the universe. Though finding them would be far more difficult than tracking the massive object at the center of our own Milky Way. All of these types, from the smallest stellar remnants to the most colossal supermassive cause, share one unifying trait. Their gravity is absolute. Once anything crosses their event horizon, it is gone from the observable universe. Yet their differences paint a picture of cosmic diversity within the category of black hole. This diversity is why astronomers do not simply study Sagittarius A star in isolation, but instead place it in the larger context of black hole research. It helps us see what is typical and what is unusual about our galactic center. How Sagittarius A got its star. From Earth's position inside the Milky Way, we can't look down at our galaxy from above. We're stuck inside it, surrounded on all sides. So to talk about different regions of the galaxy, astronomers use constellations as directional signposts, When they say something is in Sagittarius, they mean it lies in the sky within the area of that constellation. It doesn't mean the object is part of the constellation, just that it's in the same region of the sky. When astronomers looked closer in the direction of Sagittarius with their radio telescopes, they realized they were seeing a cluster of different sources, all located near the center of the Milky Way. To keep track of these signals, they needed names. Astronomer Bruce Ballack and his colleague Robert Brown were studying the central radio source in the early 1970s using high-resolution radio imaging. They were zeroing in on a compact point at the very heart of this group. They called the whole group Sagittarius A since it was the first major radio source found in that region, following the naming tradition used in radio astronomy at the time. A stood for the first discovered object in the constellation Sagittarius that gave off radio waves. If more sources were found nearby, they would be called Sagittarius B, Sagittarius C, and so on. Within Sagittarius A, Bick and Brown identified a point that looked, as far as their equipment could tell, like a central engine, maybe the core of the entire Milky Way. That's when they gave it its unusual name, Sagittarius AAR, written with an asterisk at the end. At the time, Ballack and Brown were using a coding style borrowed from atomic physics. In those fields, the asterisk was sometimes added to indicate an excited state, a version of an atom or particle that had more energy than usual. It wasn't a formal naming rule in astronomy, but it felt right. Sagittarius A was more intense, more concentrated, and more mysterious than the rest of Sagittarius A. The asterisk was their way of pointing that out. The name stuck. In the years that followed, as astronomers across the world focused more and more on this strange spot at the center of the Milky Way, the name Sagittarius R became standard. It showed up in papers, telescope logs, and research reports. Even as technology advanced and scientists grew more confident that this object was a black hole, millions of times more massive than the Sun, the name remained. In a way, it's ironic. The asterisk read aloud as star sits at the end of the name for an object that isn't a star at all. Sagittarius, a star, doesn't give off its own light in the usual way. It pulls light in, it bends space, it swallows anything that gets too close. And yet, the name gives this invisible thing a place in the map. Astronomy is full of these names. Some, like Betelgeuse or Vega, come from ancient languages. Others, like M31 or NGC 2392, are catalog numbers, codes given by people trying to list thousands of objects without using poetic titles. When scientists discover something new, especially something not visible to the naked eye, they often fall back on a mixture of tradition, convenience, and a little creativity. Radio sources, for example, are usually named by location and order of discovery. Pulses. Spinning neutron stars that send out regular radio pulses are often labeled with their coordinates like PSRB 1009-19 plus 21. Galaxies and catalogues are given numbers. Messier 87, NGC 5128, and so on. Sometimes the names are beautiful, sometimes they're just practical, but in every case, they help scientists keep track of what they're studying. In the case of Sagittarius A star, the name does more than mark a spot on the sky. The name may be simple, but that one small mark, a single asterisk, carries the weight of a galaxy. Why does every galaxy have one? The supermassive puzzle. Almost every galaxy, no matter its size or shape, seems to have a giant black hole at its core. The same kinds of massive gravitational anchors appear at the heart of spirals, ellipticals, and even many irregular galaxies. Some are bigger than Sagittarius AAR, some far smaller. But the common thread is clear. This is a rule of the universe. The first hints of this came from galaxies where the central region was unusually bright. These active galactic nuclei were giving off enormous amounts of radiation. They were so powerful that no ordinary cluster of stars could explain them. The most convincing explanation was that a supermassive black hole was feeding on gas and dust, releasing energy as the material spiraled inward. This same reasoning applied to quasars, the brilliant beacons seen billions of light years away, which are now understood to be powered by black holes weighing millions or even billions of times the mass of our sun. Once astronomers had the right tools, they began searching for signs of these central giants in more ordinary galaxies. Time after time, the evidence showed they were there, even in galaxies that were quiet and dim at the center. In some cases, the black hole was dormant, not actively consuming much material, but its gravitational pull was still measurable through the motion of nearby stars and gas clouds. It soon became difficult to find a galaxy that didn't have one. The question then shifted from, does our galaxy have a supermassive black hole, to why does every galaxy seem to have one? The simplest answer would be that these black holes formed alongside their galaxies, perhaps as a natural part of galaxy formation. One idea is that in the very early universe, clouds of gas collapsed not into stars, but directly into massive black holes, which then grew over billions of years by swallowing matter and merging with other black holes. Another possibility is that the first stars, enormous ones far larger than any that exist today, lived short, violent lives and collapsed into massive seeds, which in turn grew into supermassive black holes. A key part of the puzzle is the strange link between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, the dense central region of stars. Even in galaxies far apart in size, this relationship holds with surprising precision. This suggests that black holes and galaxies influence each other's growth. If the black hole feeds aggressively, it can produce winds and jets that push gas away, slowing star formation in the galaxy. If the galaxy forms more stars, more material might eventually fall toward the center, feeding the black hole. This two-way relationship hints at a deep connection in their evolution, but no one fully understands how it works. The timeline of formation is also murky. Astronomers have found quasars powered by billion solar MAE,